Okay, so anyways, that's what you're calculating. When you calculate derivatives of functions at points, like f prime of a for some value of a, in this case it was a equals 1, what you're really calculating is the slope of a tangent line. Okay, so what about if you wanted to take it a step further? So like this example, which says find the equation of the tangent line to the graph of f of x is equal to x squared. So our function is f of x is equal to x squared. We want to find some information about the tangent line, but in particular we want to find the whole equation of the tangent line, not just the slope. And in particular it's at the point 1, 1, so at this particular point, right? Because of course, if you weren't given a point, you wouldn't know what tangent line they're talking about, because the tangent line depends on the point. So that's why that information has to be given. So we're going to start by finding the slope. And let's just draw a picture. Actually, I won't bother with the ruler. I'll just draw this carefully. Here's what you're actually looking at, right? So f of x is equal to x squared. This graph's going to look something like this. It's a parabola, and at the point 1, 1, we have something like this. So what we're really looking for is the equation of this line. That's what we want to find. We want to find the equation of that tangent line, right? So that's what I mean by this point was important. If this point wasn't given, how would you know you're talking about this tangent line? Because if I picked another point over here, it'd be a different tangent line. So the actual point you're looking at matters. Okay, so, well, we'll start by finding its slope. And we'll do it in the exact same way we did it in the previous example. We're going to actually need to find f prime of 1, again in this case, because the x-coordinate of this point is a 1. And that's what tells you that you're going to plug 1 into the f prime of a notation. So we're going to start by finding the slope. So begin by finding the slope. You're going to see this question, or questions of this form, lots in this course, and in particular in chapter 3. You're going to see this sort of a question asked a lot. What will change is the type of function you're dealing with. You'll gradually get more and more complicated functions, but it'll just be of the form. You have a given function, and you have a given point on the graph of that function, and you want to find the equation of the tangent line. So that's something that you want to get mastered early, because you're going to it's a lot of free marks, because you're going to have to answer that same question over and over again, but just with more and more complicated functions. But it's important to get the general flow of the solution down early on. So you want to begin by finding the slope. Okay, so we'll take f prime, and then whatever you put here is going to be the x-coordinate of that point. So we want f prime of 1. Okay, so, well, start in the same way. The limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. Okay, so just using this definition right here with a equal to 1. It's just a coincidence that we're using 1 again, because 1 happens to be the x-coordinate of this point, right? So it's not, we don't always do 1, right? It's going to be the x-coordinate of whatever point you're interested in. So in this case, we're going to put a 1 here, and that's why the 1 went here and here as well. Okay, well, let's actually evaluate this a step further. Unwind what the function does here now. So this is going to be the limit as h goes to 0 of 1 plus h squared minus 1 squared, right? Because this is f of h, or pardon me, f of 1 plus h, and this is f of 1. Okay, so that's all going to be divided by h. And so what are we going to do? Well, if we plug in h equals 0, we're going to get 1 plus 0 squared, which is just 1 squared minus 1 squared. So you'll have 1 minus 1 on the numerator, which is 0. And h equals 0 on the denominator, you're going to have a 0 over 0 type. So we have to do something. We can't just plug in h equals 0 at this stage. But there's work that's kind of begging to be done here, right? We've got, this is kind of like a quadratic in h. And then we're subtracting this 1 squared, which is really just 1. You're subtracting 1 afterwards. So why don't we expand this out and then combine it with this minus 1 and see what happens. Like this is a pretty good sign that there's something to be done up here. So why don't we play around with the top and expand everything out and simplify. So we'll have the limit as h goes to 0. If I expand the brackets out here, I'll get 1 plus 2h plus h squared. And of course 1 squared is just 1, right? So that's why I wrote minus 1 afterwards. Okay, well 1 plus 1 and minus 1 over here are going to cancel. So really the next step, this might clean up quite nicely. We're going to have 2h plus h squared over h, right? And now I've kind of run out of room going down, but I can now work my way over here, and I think I'll have enough room to finish it over here. Now that those 1's canceled, now there's a common factor of h here in the numerator. So why don't we factor out an h? So I can factor out an h, and I'll get h times 2 plus h all over h. And hey, guess what? Now we got a common factor of h to cancel out. So we've got the limit as h goes to 0 of 2 plus h. Well, hey, 2 plus h is a continuous function of h. We can just plug in h equals 0 and get a slope of 2, or the limit will evaluate to 2, which is, this is the slope of our tangent line, because that was f prime of 1, which is the slope of this line. So this line has a slope of 2. So we're well on our way to finding the equation of this line, because there's really not much more to it. Because what do you need? To get the equation of a line, what do you need? You need the slope, and you need, well, if you have the y-intercept, that you can write the line in the form y equals mx plus b. If you don't have the y-intercept, but you do have a point that the line goes through, that's good enough. You can use it to find the y-intercept if you want. That's an option. But you can also just write down the tangent line immediately. If you have the slope and you have a point that the line goes through, that's enough to immediately write down the line. So we can sneak it in down here. The tangent line is given by, what's the equation of a tangent line? I'm going to write down the formula up here just to remind you. This was mentioned on the second lab worksheet, but the formula for equation of a line in point slope form is y minus y naught is equal to m times x minus x naught. Okay, that's just a reminder of the formula. I'm not going to write down all the context. I'm going to say it out loud. But just that's a reminder. That's the equation of a line with a slope of m who goes through the point x naught, y naught. So x naught is the value that goes here, and y naught is the value that goes there. If you put those two numbers together as coordinates into a point, you get a point that the line goes through. Then this is going to be one way to represent that line. So in our case, we've got the line that goes through this point. We've got a slope of 2, so we can use that point slope. We can use this point slope form, to write down the equation of the line. So we're going to get y minus 1, because the y naught, I keep pointing off the page, y naught is 1 and x naught is 1. Let me clarify. So this is our x naught, and that is our y naught in this formula. And then this is, of course, is our m. Okay, so we're going to get y minus 1 is equal to 2 times x minus 1. So that's really your tangent line right there. Okay, so that's how you can find an equation of a tangent line. Start by finding the slope, and you're going to use the derivative of the function at the particular x value of interest to do it. Once you have the slope, you can get the tangent line. So a fact here that's worth knowing, and it's worth mentioning early on, is that if you have a function f that's differentiable at a particular point a, that's really what we start with here. So if f is differentiable at x equals a, then f is necessarily continuous at x equals a. So in other words, if you know your function is differentiable at a point, then you already know it's going to be continuous there. But now this says the converse is not always true. So what do I mean by converse? Let me clarify that now. Converse, in other words, i.e. the reverse implication. Okay, so what we are saying here is there are functions which are continuous at a given point but are not differentiable. And I'll just say continuous but not differentiable. But what I mean by that is it's easy to come up with a function and a particular point in the domain of that function, where that function happens to be continuous at that point, but not differentiable at that point. And in the next video, I'm going to give you an example of that.